Hello, everybody, and welcome to another exciting episode of General Biology 1. Today, we're going to talk about water. You know it, you love it, but you may not know what it's capable of doing, not just yet. So, I've always been interested in aliens and astronomy and things like that, among my other hobbies, of which I have many. And it's interesting how the search for life on other planets, like this one here, Mars, often involves searching for water. Right? And there's a reason why people look for water in space. Because life as we know it is very difficult to understand without thinking about the presence of water somewhere in that picture. This is true at the big scale of ecosystems and ecology, but also at the individual scale and the cellular scale, right? How animal physiology works, plant physiology works, the cell, right? So the search for water, in many ways, is the search for life. So we'll talk a little bit about what water is, and this should be pretty straightforward. We've already talked about it at this point. So here are some water molecules that are interacting, right? Is this a polar molecule or a nonpolar molecule? Well, we know water is a polar molecule, right? Based on its covalent bonds. It even says it on the picture. Now, what type of shape do these polar covalent bonds make water, H2O? Yeah, a bent shape, right? So what type of bonds are present? Well, of course, there's the covalent bonds that hold water together, and these are polar, meaning that they share their electrons, but they do so unequally. But they also form these other bonds, right? Hydrogen bonds, which are based on differences in the delta. What does that delta symbol represent? Yeah, it represents the slight charge difference based on that sharing of the electrons. And the delta itself is what we use to indicate the dipole. So there's a negative dipole, there's a positive dipole, and they tend to orient each other because opposites attract, forming the hydrogen bond. Now, I told you before that hydrogen bonds are the most important thing that you never thought about, but I didn't really tell you why. That's where this class comes into. Okay, so where's the water? I'm sure you know that most of the Earth's surface is covered with water. You know that most of you is water. You know that most of the Earth's surface is covered with water that's not quite drinkable because it's salt water, right? So less than 3% of the water that we know of on this planet is fresh water. So what's that fresh water? Well, you have the lakes and the rivers, right? Your Great Lakes, whatever lake you happen to know, rivers, Mississippi River, Nile, Amazon. Okay, those are all together represent less than 0.3% of the water on the planet. So these are your surface waters. You also have a substantial amount underground, right? Swampy areas, your groundwater, the moisture in the soil, right? The water table. If you go far north or far south enough, a lot of that is locked up permanently in what we call permanent permafrost, right? So this is just basically frozen water in the ground. So that represents a good chunk. And then the majority of it is in some sort of permanent snow cover. So you're probably thinking Antarctica, maybe Greenland, the islands of the Arctic, these large continental glaciers, as well as a lot of the smaller alpine glaciers that are scattered throughout the world's mountains. So that's about just under 70%. And there's water in a few more spots. There's some water in our atmosphere. It comes and goes, highly variable, but it doesn't represent a large chunk. So I want you to think about that 3% fresh water. That's not only our drinking water, but it's also the water that we use to power our industrialized society. If you think about pipes, they have to be specially fitted to move salt water around. Our machines that need to cool, our refrigerating systems, all these things require fresh water, right? You can't have salt water. Salt water can corrode things. So you realize we don't have as much water as we think we do, and definitely not as much water as we act like we do. And water, of course, is important for a lot of reasons. And in many ways, water determines what kind of ecosystem you're going to be living in. So here's a water molecule again, kind of showing it in an interesting way with the electrons and how they're shared. It's kind of cool. Now, water molecules will stay in something for only a short period of time. And what I mean by that is there's what we call these residence times or retention times. And how long they stay in something has big implications for what can happen. So here are the residence times for water molecules in a variety of sources. Notice living organisms, the biospheric um, time for water is about a week. So think of yourself. Think about how often you go to the bathroom, right? And you get rid of water, right? You call it something else, but it's basically water, like most things. You're getting rid of that water. Well, in 1 week, you'll have gotten rid of the equivalent of whatever the volume of water is in your body at a given time. That's interesting to think about, right? In the atmosphere, it's about a week and a half. Rivers, of course, they're flowing out into the ocean, so they're getting rid of a water molecule every 2 weeks, right? So enters in at the source and gets out in 2 weeks. That's how long a water molecule spends time in a river, right? Now, when you start getting to some of the other extremes, right, you're looking at a water molecule can stay in the ocean for 4,000 years. It could stay in the groundwater for up to 10,000 years, right, depending on how deep that groundwater source is and whether it's being fed by something. And notice glaciers and permafrost, the stuff that we often talk about with climate change, for example, that retention time is very, very long. So those water molecules that are present there have been out of action for quite a while and now are getting liberated. Question is, can our systems handle it? So water is moving through ecosystems, and as they do this, they determine the rate with which things happen, right? Obviously, they determine things like how fast plants are going to grow, how many plants are going to grow, how productive it's going to be. But it also determines things like the integrity of the soil, right? What are the rates of erosion? How fast are things going to decompose and break down into nutrients, right? These are all extremely important aspects of ecology in an area, and yet water seems to be the determining factor for how fast and how short and how long these processes are going to be taking place. So the difference between a desert and a rainforest is water, plain and simple, right? They're both hot, but they differ in their water, and yet are the two most different environments you could think of, right? So let's look at the rates of nutrient cycling in a little more detail. This is a map showing the distribution globally of decomposition rates of leaf litter in an environment. So notice the places that are very red, orange in color, these are places where litter decomposition happens very quickly, right? So if something falls on the ground, it's going to break down and become part of the soil much, much faster than in those areas that are blue. And notice those blue areas, right? They include not only Arctic areas, but they also include places like deserts, right? If you look at Greenland, right, there's very low decomposition rates there, but there's also very low decomposition rates in the Sahara in northern Africa there, both of which are shown as up as purple. And what determines the difference is the rate with which water shows up, and that sets the pace for how much nutrients are going to be cycled. And usually when we talk about this in an ecosystem fashion, we're talking about precipitation, right? Rainfall. So the rates of nutrient cycling are determined by precipitation, and in places where there's a lot of rain, too much rain in fact, often depletes the soil simply because the constant rain is moving through the soil, and as it moves through the soil, it pulls those nutrients out. So it often leads to very poor soil, right? And yet very rapid rates of decomposition. So a rainforest, for example, would be an example of this. And one of the reasons rainforests are in such trouble is because people want agricultural land. But in rainforest environments, most of the energy, most of the carbon, most of the nutrients are actually above the ground because the soil is actually pretty pure. And because it's poor, they have to burn the trees down and do that slash and burn agriculture in order to enrich the soil. Otherwise, if they just pulled all the vegetation out and started planting, they would have a very poor yield because the soil is so poor, because those nutrients are constantly getting leached out by the constant rain that happens in these places. On the other hand, if you talk about a temperate forest, so something, let's say, like Northeast US, right? Somewhere around like, I don't know, New York, Massachusetts, Pennsylvania, places like that, or in the Midwest, the soils there are much better. There's less rain, and because of this, there's still rain, enough to support plant growth, but the rain is much less frequent, much less intense, meaning that most of those nutrients stay in the soil. But if you look at the decomposition rates, they're going to be a lot slower in a place like that. So water is extremely important, which I know, stating the obvious. I know. Moving on. Water is going to move through an environment, and it's going to move through it. In any given moment, it can be anything. You know, it can be a solid, you know, it can be a liquid, you know, it can be a gas. And collectively, we talk about the water cycle. And the reason it's a cycle is because a water molecule is moving through all of these things at whatever given rate it's moving through them. And at any given moment, it can be any one of these things. And it's a cycle because it's complete. So every water molecule is accounted for in the cycle. Nothing's being added. No new water molecules are being created out of thin air. Nothing is being taken away. So you know these things already. But just in case, you have precipitation. We call it rain. Could also be snow. It falls on ground surface. A lot of that just flows on the surface of the earth. That surface runoff. A lot of it makes its way into groundwater sources, right? It recharges these groundwater sources. Surface runoff tends to run into some sort of freshwater body, a river, or something like that, which then flows out to a lake and out to the ocean. And in these surface bodies, you'll get the evaporation, right? You know this. It'll become a gas. It'll make its way up into the atmosphere. As it goes up into the air, it starts to cool, right? And it can condense into liquid form and start the process all over again. At the same time, you're also losing water from plants that are using water as their metabolism. One of the byproducts is they release water into the atmosphere, right? We call this transpiration. We'll learn a lot more about that in the future. So these hydrogen bonds, I told you they're the most important thing you've never heard of and never thought about. And they are absolutely essential to the properties of water that allow life to exist on this planet and probably others as well. I can't verify the latter statement though. So the four major properties of water are all a product of hydrogen bonds. And it's this thing that makes water unique. There's a lot of liquids out there, but water remains the unique liquid because of these hydrogen bond and their properties that they bestow upon water. So these four are cohesive behavior, the way it interacts with temperature, how it responds to freezing, and how it can act as a solvent. So let's start with the first. So this is a basilisk lizard. They're found in Latin America, in the rainforest, and you see it's running across a body of water. This could be a lake, a river, it could be deep, but it's able to do this because much like the geckos we've already talked about, they have feet with really wide surface area. But this lizard, which because it's able to run on water, gives it its other nickname, the Jesus Christ lizard, is able to do this on water and water alone. So if it tried to run across, say, a vat of alcohol or something like that, it would not be able to do this. It is only water that can sustain a lizard running across its surface, right? So this is a product of cohesive behavior, again, because of these hydrogen bonds. So if you look at a tree, I've always been amazed by this. How does water get up to the top of a tree, right? Water, you water a plant at its roots and then pulls it up to the top and to the leaves. Great. And we'll learn a little bit more about this. Water is the thing that can do this. Other substances can't do this. A tree or plants in general, they use their xylem as sort of like a water conduction system, like their circulatory system. And it's the properties of these hydrogen bonds that bestow two things that water molecules can do. They have a very high tendency for cohesion and a very high tendency for adhesion. So what's the difference between cohesion and adhesion? Any ideas? Well, you probably know from adhesive, it sticks things together, right? So when we talk about adhesion, we're talking about the ability of water molecules to stick to things, right? Stick to the inner surface of a pipe, stick to the inner surface of the xylem in these plants, right? So that's the property of adhesion. Cohesion, like when you're in a group and you're a cohesive group or a cohesive team, that means you're working together, right? Cohesion is these hydrogen bonds keeping those molecules together. So think of it as like a chain. One water molecule goes up and it's pulling the next water molecule up, which is pulling the next water molecule up. And it's doing this with hydrogen bonds. Right? Very incredible. They work together really well. This not only happens when you're looking at a plant, but it also happens on the surface of a water body where it forms surface tension. Again, a product of the cohesion of these hydrogen bonds. So here's a jaguar poking its head out of the water. It's completely surrounded by a film of water. Well, the reason that film is able to stay intact like that, at least for the moment, is because of that high surface tension. Right? And this is a spider. It's a fishing spider or diving spider. It actually uses surface tension to create a bubble of air underneath the water. So it actually will go in and its lungs are on its abdomen. It has these book lungs, they're called, which is what spiders have. And it will back its abdomen in there and actually take a breath. And then it will go up to the surface every now and then replenish it with air. Well, you can keep an air bubble underwater because of the properties of surface tension produced by hydrogen bonds, right? If you've ever been in a canoe that flipped over, I've been in a canoe that flipped over several times. You can get under the canoe and you'll find under the canoe that it's actually there's still air there, at least for a little bit, right? Or in a boat, right? Could be a potential thing that saves your life in a bad situation, right? Again, it's that surface tension that keeps the water from entering into the boat. That air to water where they meet, that interface, stays very much intact because of the surface tension. Again, hydrogen bonds. So that's the first property. What about the second property? So I'm sure it's no surprise to you that as you get closer to the coast, anywhere, it tends to be a little bit cooler on hot days. It also tends to be a little warmer on cold days. And the reason is because it actually takes a lot of energy to change the temperature of water. So this is a picture from your textbook, I believe, showing Los Angeles and areas around there, San Diego, Santa Barbara. And you see a low, nice, comfortable 70s temperature right along the coast. But as you move further away, by the time you get to Palm Springs, you're in the desert, you're drastically increasing your temperature because you don't have that moderating effect of the ocean, right? The Pacific Ocean there has a cold current that runs along it, helps to cool the environment. So water helps to modulate temperature. It keeps it from flowing so much. And we call this the specific heat capacity of water. And specifically, it defines the energy that's required to increase 1 gram by 1 degree Celsius, right? So 1 gram of water by 1 degree Celsius. And we actually use this to define a unit that I'm sure we all know and love, the calorie. So that's the definition of a calorie, in case anybody ever asked you. 1 calorie is the amount of energy it takes to increase a gram of water by 1 degree Celsius. So probably never thought of that, did you? That's what a calorie actually is. It actually has to do with how much energy you need to increase water. So why is this an important property? Well, it's important because of what's happening in the world today, right? We're seeing all these drastic changes with regards to increasing temperatures. Well, coastal environments, even though they're at risk of flooding, are going to be a lot less variable than those that are further away from the coast in terms of raw temperatures. That's why you're hearing a lot about heat waves in the interior of the continent, right? In like the prairie states here or in the interior of Europe, right? It's also going to be a concern because as you increase temperature, you're also going to increase evaporation. So you're going to get more water into the atmosphere. Who knows what that's going to impact down the line. But moderating temperatures is one thing it does at the ecosystem level, but it could also do this at the individual level. Because water not only has a high specific heat capacity, but it also has a high latent heat of vaporization. So that specifically is the term used to describe the amount of energy required, or the amount of energy that can be absorbed by water to convert 1 gram of it into a gas, right? So instead of energy required to raise the temperature by 1 degree, it's the amount of energy required to turn 1 gram of a liquid, like water, into a gas. That's important. How does sweating cool you down? This is Kobe Bryant. You might have heard of him. How does sweating cool you down? He's sweating. He just played basketball, right? Didn't just do that, I should say. But how does sweating work? Well, the idea behind sweating is that you're taking water from your interior and you're putting it on your exterior so it can evaporate. But water that was in your interior is also going to soak up heat energy in the interior of your body. And it will carry that heat energy out to the surface of your skin where it's going to evaporate. Okay? So that's what sweating is. Sweating is literally transferring the heat from inside using water to the surface, which then evaporates and goes off into the ether. So it's a wonderful thing, right? At this point, I usually would make a joke about Kobe Bryant, but I don't think it would fly. Okay, that came out wrong. We could all agree that he made an impact. Okay, moving on to another sport. Being Canadian, I have to give props out to my two favorite teams here, the Leafs and the Canadians. So hockey is only possible because of our next property of water. And that next property is this. When water is in liquid form, those water molecules are moving around, right? Those hydrogen bonds are breaking and reforming as the water is moving around physically. But as temperature starts to decrease, the kinetic energy, the water molecules moving around, starts to slow down. And as they start to do that, those hydrogen bonds aren't breaking and reforming again, and instead start to stabilize. And in doing so, just like we talked about with salt, they form a regular pattern, what we call crystals, right? Ice crystals are exactly that. Water molecules forming this regular pattern. And as you can imagine, it's those hydrogen bonds, right? It's those dipoles, those positive and negative dipoles interacting as they are to create this regular pattern that is then the ice crystal. Well, here's an interesting thing. You've probably been taught all throughout your life that liquids, the liquid molecules are at a certain density, but then as it starts to solidify, they reach a higher density, right? They become more dense. Solids are more dense. Solids tend to be the heavier form, right, as compared to liquids or compared to gas, right? Gases, those molecules are very far away from each other, right? It's a very low density. Liquids, they tend to be a little closer. And then by the time you get to a solid, they tend to be a lot closer, higher density, making them a lot heavier. Not quite the case with water, though. It's the exception to the rule. Why would this be important for life? It allows hockey to happen. It allows this shrimp on your picture to happen. Think about it up north. Probably don't want to think about Florida because it never happens here. Well, I remember as a kid, I was into skating, I was into hockey, and we would skate on the local lakes. And it was kind of crazy. We'd even skate on like Lake Ontario, one of the Great Lakes. And it was crazy to me to be like zipping around on the surface of something that's like, could be like 50, 100 feet deep, right? And I was just fine, middle of winter, skating around, right? Doesn't happen as much now. The reason I could do that, well, by stabilizing these hydrogen bonds, it keeps the water molecules a little further away from each other, meaning that it's less dense than water. If you're going to drink water and you throw an ice cube in there, that ice cube is not going to sink to the bottom like it would with any other solid form of a liquid. Instead, it's going to float to the surface. Ice floats. If ice floats, the life in a pond, the life in a lake, the life in the ocean could stay put, be safe, buffered from the outside environment, right? Imagine what the world would be like if things froze from the bottom up. Well, in a cold year, your lake would freeze from the bottom up, forcing all that life to the surface where it wouldn't make it, right, in the winter. So the fact that ice freezes from the top and floats allows life to continue. It's amazing. It's really amazing, these things. Okay, so let's talk about something else. This is a sugar cube. It's thrown into some water, and it's doing what sugar does. It dissolves. Let's use some terms here. What is a solvent? Which of these three represent the solvent? Okay, hopefully you picked up water is the solvent, right? So water is the solvent because it does the dissolving. Sugar in this case is the solute, right? Solute, because it dissolves, right? So water is a solvent, sugar is a solute, and water and sugar together form a solution. And that's what a solution is. It's something dissolved into a liquid. So water as a solvent, it's really good at what it does. It's versatile. It's sometimes called the universal solvent. And anytime something dissolves in water, it becomes an aqueous solution. And the reason it's really good at dissolving things is, again, because of the dipoles that are formed from the polar covalent bonds, right? It's got a high polarity, so it allows it to form what they call hydration shells or hydration spheres, right? So anytime it's exposed to something, whether it's positively or negatively charged, it's able to dissolve it. Well, if you have something that's able to dissolve easily, we often refer to it as being hydrophilic. But if you have something that's a little more difficult to dissolve, we talk about it being hydrophobic. And if you recall, when it comes to nonpolar molecules, they don't exactly mix, right? So a nonpolar molecule is one where the covalent bonds have the electrons being equally shared, meaning that there's no charge difference. And if there's no charge difference, well, that means that those hydration spheres can't necessarily happen. So we could talk about them being hydrophobic, afraid of water, as opposed to hydrophilic, that likes water. So since we're on the topic of chemistry, let's ask some really simple, hard questions. In chemistry, what do we talk about when we talk about an amount? Well, an amount in chemistry simply refers to a quantity of matter, right? And it really depends on what our units are. Is it a mass? Is it a count of units? It could be anything, right? So that's what an amount means. Now, what about volume? So when we talk about a volume, what we're really talking about is the amount of space. And we talk about volume as a 3D thing. If you recall, volume is usually like, centimeters cubed or something like that, right? So it's a 3D space, and it could represent a liquid, it could represent a solid, it could represent a gas, right? So one's a quantity of matter, one is a 3D quantity of space. And a concentration, well, it's simply the amount per volume, right? So we talk about milligrams per milliliter, units per liter, grams per liter. It could be anything, right? So those are three concepts that you kind of know. So they're simple, but they're also kind of hard to explain, which is often the case with a lot of these terms, right? You know it when you see it, but they're hard to explain. So now we're going to talk about another unit that's kind of important in chemistry. This is going to be part of your quantitative sort of skill for this unit. And that is, what is a mole? So a mole is a cute furry animal that lives underground, okay. Kind of blind, okay. But in chemistry, a mole is a very specific number, what we call Avogadro's number. Don't have to know that. But you do need to know that it represents the number of molecules. And what's the number of molecules? It's 6.022 times 10 to the 23 molecules. So when you have a mole of something, that means that you know exactly how many molecules are in that thing that you have. So this is important because we use this we use this in chemistry in order to do reactions properly, right? So when we talk about the molecular weight, what we're really talking about is is what is the weight required to get a mole of something. So what am I talking about? Okay, so here's an example. Let's pick water. So water is H2O. You know that there are 2 hydrogens and an oxygen in water. If you look at the atomic mass of hydrogen, it's 1.0079. Let's just say 1. If you look at the atomic mass of oxygen, the atomic number is 8, but the atomic mass is 15.999. Let's just say 16. So the atomic mass of hydrogen is 1, atomic mass of oxygen is 16. So the molecular weight would be 16 plus 1 plus 1, which is 18. So that's the molecular weight. But who cares about the molecular weight? You want something more real than the molecular weight. Well, the other way to think of it is if you have 18 grams of water, you basically have 6.022 times 10 to the 23 molecules of water. So 18 grams of water is equal to that number of water molecules, which means 18 grams is equal to 1 mole of water. And that's the goal, to figure out how many grams are needed to make a mole. And when we talk about mole, we're talking about usually not necessarily mole, which is the number of molecules, but we talk about it as a concentration and use the term molarity, meaning how many moles are found in something. When we talk about molarity, we usually symbolize it as a capital M, and that represents moles per liter. So the concentration of a substance dissolved in water, what is its molarity? What are the number of moles of that substance per liter of water? So let's do another one, right? Let's do sucrose. Sucrose is made up of glucose and fructose, 2 different simple sugars that are joined together. Don't worry about that right now. But if you were to count up all the carbons, you would have 12 carbons. You would have 22 hydrogens, and you would have 11 oxygens in a molecule of sucrose, right? So if you were to add up all of the molecular weights, so 22 times 1, 22, 12 times 12 times 12, 16 times 16, or sorry, 11 times 16, and you were to add all those up, you would get 342. So 1 mole of sucrose, to get 1 mole of sucrose, you need 342 grams of sucrose. Now, if you have 342 grams of sucrose and you dissolve it in 1 liter of water, you would have a 1 molar solution of sucrose. So again, you have a mole of sucrose. That's just the molecular weights added all up for all the varying atoms. You add them up, you take that number as a gram, or as grams, and then you dissolve it in a liter of water, and that gives you a 1 molar solution of sucrose. Hopefully that makes sense. Let's try something else. So that's a molar solution of sucrose. 342 grams of sucrose dissolved in a liter is a molar solution of sucrose. So how many grams of sucrose would you have to add to 1 liter if you wanted to make a 0.5 molar solution of sucrose? Okay, well, hopefully you figured out the trick, right? You still have a liter of water, so the volume hasn't changed. But you want to make a half molar solution of sucrose? Well, if you need 342 grams to make a molar solution, well, if you do half as many grams, you're going to get a half molar solution. So the correct answer here would be A, 171 grams. So the thing about solution molarity and solution making is to remember some useful tips. Molarity is a concentration, right? It's a moles per liter. But it also helps to think of it as a fraction. It also helps to think of it as a ratio. Often the types of solutions you'll be making will be, you know, um, sort of sort of standard, right? You'll make a 5 molar solution, a 1 molar solution, a half molar solution, right? And because of that, it's very easy to go back and forth between them if you can think of them as a ratio or a fraction. So a 5 molar solution, well, that's 5 moles per liter. It's 5 moles per 1 liter. That's also 2.5 moles per half liter, or 2.5 moles per 500 milliliter. And that last one uses us into tip 2, which is you need to get acquainted with the metric system if you're not already. The metric system is the language of science and makes a lot more sense, frankly, than the old British imperial system. And everything's on the scale of 10, so it's basically what they call a logarithmic scale. So here, for example, are some of the key ones that we use. Can't say I use mega very often, but you know, changing between a kilo and a liter and a milliliter, microliter, centiliter, those are things that happen pretty obviously, or pretty often, not obviously. So tip 1, tip 2, something to get you started on your quest towards making solutions yourself. Now, let's just say you wanted to get crazy and you want to figure out the molarity of 85.5 grams of sucrose when it's dissolved in 250 milliliters of water. We'll take a second. Well, hopefully you got the trick. So if you know anything about the metric system, you know that 1 liter of water is equal to 1,000 milliliters of water. So that's the volume conversion. So if you have only 250 milliliters, well, you're basically looking at a volume that's a quarter of that. We know that for sucrose, you need 342 grams of it to make a mole. In this case, you have 85.5 grams of sucrose, which, if you did the math in your head, would realize that it's a quarter of the amount of sucrose that you would need to make a mole, right? So it gives you a quarter of a mole. Well, a quarter of a mole into a quarter of the water doesn't change anything. Again, it's a ratio. So the correct answer in this case is you would produce a molar solution. So the correct answer is B, because you've added a quarter of the sucrose to a quarter of the water. Now, had you added it to, the quarter of a sucrose at 85.5 grams and you added that to 1,000 mils, well, then you would have a 0.25 molar solution of water, right? Because it'd be diluted. But because you changed both the sucrose mass plus the volume of the water, both the same amount, everything stays constant. So it's a 1 molar solution. So here's the other thing, and this is where chemists and biologists sometimes differ. When we talk about biologists and volumes, we're often working with very small amounts, right? Very small concentrations, millimolar solutions, micromolar solutions, right? And these are the abbreviations for it. Micromolar has the Greek letter mu for its value, right? So you take the capital M, you put a little lowercase m or a Greek m in its way, right? So the thing to remember is that if you're dealing with things like a millimolar solution, for example, the volume stays the same, right? It's still a liter of a solution. It's just that the matter amount or the molar amount is less, right? So 1 millimolar solution is equal to 1 millimole in 1 liter. Not 1 millimolar solution is not equal to 1 millimolar in a milliliter, right? So the volume stays the same regardless. And this leads us to the next important thing you need to understand. And it definitely is worth going over this quite a bit. This is the solution chemistry that is the most important thing you're going to need for a biology class and probably a good number of chemistry classes too. And if you don't already know this formula, you might as well just memorize it, get it tattooed on your forehead. C1V1 equals C2V2. Usually what happens is you're given a concentration at the start and you need to produce a new concentration. Or you're given a volume at the start and you need to produce a new volume. This is the relationship between them that allows you to figure out the ratio. And if you have three of the four, C1, V1, C2, or V2, you can calculate the missing one based on this equation. So it tells you how much solution you need or how much volume of a solution you would need. So C obviously stands for concentration, V obviously stands for volume. You have a starting concentration, which is usually your C1, V1, or your C1 or your V1 for volume, and then what you want is the C2 or the V2. It doesn't kind of matter, to be honest with you, as long as you keep it consistent within the equation. So this is kind of a classic example, right? Here you have solutions. You want to make a diluted solution, but you have a stock solution. A stock solution is usually highly concentrated, much more than you could ever use for an experiment or for whatever it is you happen to be doing, right? So in a concentrated solution, you have a very small volume, but you have a lot of the molecules in there. You want to make a dilute solution where you have more volume and you don't need it to be as concentrated. So often we talk about the concentrated solution as a stock solution, right? It's the thing that you make your other solutions from. So let's say you have a stock solution of 10 molar sodium chloride, right? So it's 10 moles of sodium chloride in a liter of water, okay? But you need a solution that is 2.5 moles of sodium chloride, and you need to make 350 mils of the stuff. So this is a standard question. How much of your stock solution are you going to need? And how much water are you going to need to make the solution that you want, the 350 mils? Well, right off the bat, you have a starting concentration. You know that 10 moles is your starting concentration. So that's your C1. You might want to write this down. So C1 is 10 moles or 10 molar. You have a C2 because you want 2.5 moles, right? So that's going to be your C2. And you also have a V2, which is 350 mils, right? That's what you want as your final solution, right? You want 350 mils of this stuff. So then the question is, okay, you have your C1, you have your C2, and your V2. So what you're going to be doing is solving for V1. So how do you do this? Well, you basically rearrange the equation, right? So C1 V1 equals C2 V2 becomes V1 equals C2 times V2, and the result divided by C1. So what's 2.5 times 350 and then divided by 10? I won't bore you with the math, but if you do 2.5 times 350 divided by 10, you get 87.5 mils, right? So that tells you that's how much stock solution you need, okay? So now you know that V1 equals 87.5 mils. That's your stock solution. So if you add 87.5 mils, you still don't have 350 mils. So what you would do is you would then add the difference as water, right? Because you're making a solution. So 350 minus 87.5 would be 265.5. So you would need 265.5 milliliters of water, and then you would add 87.5 milliliters of your stock solution of NaCl. And that will give you 350 mils total of a 2.5 molar NaCl. Easy stuff, but you definitely recommend you doing some practice, and there are some practice worksheets on Canvas, of course. Okay, so let's talk a little more about water. So water is a very stable molecule, but it's not 100% stable. It actually sometimes dissociates, and it occurs very infrequently, but it's very important. So what happens? Well, two water molecules meet, and every now and then what will happen is one of those hydrogens will transfer from one to the other to form essentially like almost like an isotope, right? So you have H3O plus, right? It has a plus now because it's gained an extra hydrogen, which is a positively charged. We call this a hydronium ion. And then the other one lost hydrogen, so it becomes a hydroxide, OH minus. Now, OH minus is a pretty stable thing. Hydroxide is a pretty stable thing. But hydronium is very unstable, right? So what ends up happening usually is the hydrogen then leaves on its own and becomes sort of freely dissociated. Now this reaction occurs in pure water. It's very rare. 1 in 554 million molecules do this. But it occurs, and it's reversible. So it's occurring at any given moment. If it occurs too frequently, what happens is it changes the properties of that water. So under typical circumstances, in a 1 molar solution of water at 25 degrees Celsius, at any given moment, based on this frequency of dissociation, your concentration of free hydrogen ions will match your concentration of free hydroxide ions. And they're about 1 times 10 to the negative 7 mole. So that's 6 zeros, that's 0.6 zeros, and then a 1 moles, right, or molar solution in 1 liter of water. That's how much it's happening. And the H plus and the OH minus are equal to each other. That 7 is important, right? That exponent with the minus 7 is actually very important because that is what we've decided is neutral. That's what we call neutral. When something sways from being neutral and you start producing too many H pluses or protons, they're just free protons because you lose the electron. You start producing too many protons, well, you start becoming an acid. If you start gaining too many protons and you start getting too many OHs, it becomes a base, right? So this is the how we've defined the acid-base scale. When we talk about the acid-base scale, what we're talking about is the pH scale. So what is an acid? An acid is anything that gives up a proton. So hydrochloric acid, HCl, well, the reason it's hydrochloric acid is because under normal circumstances, it's very willing to give up that proton and then produce, not only a hydrogen proton, but also Cl minus, right? So it has a tendency of losing it. That makes it an acid. As opposed to something like ammonia, NH3, which is a base because instead of losing the proton, it acquires it. So ammonia, in the presence of a proton, rapidly becomes ammonium. So it's an example of a base or an alkaline solution. Now, under normal circumstances, you want a balance of both, right? Bases can take things out of solution and can act as a buffer to acids and vice versa, right? So here's a scale showing the pH scale, showing where water is, and water at its purest form is at a 7. Notice human blood is a little below that. Generally, as it works, the smaller the number it gets on the pH scale, the more acidic it becomes, the larger it gets, the more basic it becomes, and the scale goes from 0 to 14, right? So under normal circumstances, when we want to figure out the pH of something, not normal circumstances, the pH scale is basically a log scale, and it's a scale of how many protons there are. When we talk about a log scale, we're talking about something that is that changes very, very large degrees by tens as you go from one scale to another. So what does that mean? Well, that means that something that is at a pH of 6 is 10 times more acidic than something at the pH of 7, right? So Something that's a pH of 5 is 100 times more acidic than something at the pH of 7. So pH is actually just the negative log of the concentration of hydrogen protons. Right? So in the case of regular water at its purest form, if you did the negative log of that, you would find that you would just get the exponent. So it would be 7, which is your neutral. Right? So that's the little thing in the box there. So it's important to remember this, right? Log scales are pretty crazy, right? It's like the Richter scale for earthquakes. It's the same thing, right? An earthquake of a magnitude 6.0 on the Richter scale, right, is not that bad, frankly. But something on the Richter scale of 7.0 is 10 times worse than a 6.0 earthquake, right? So those log scales are pretty intense, right? They're based on very big differences. So that's what pH is. So some common household products there. Gives an idea of, I drink a lot of black coffee, so I'm making myself very acidic on purpose, I guess. But moving right along, right? You have acids, you have bases, they're out there, they do things, but there are things that can protect you from acids and bases, right? And this is where buffers come in. A buffer is anything that helps to bring you back towards a neutral, helps to equilibrate exposure to either an acid or a base. So a weak base, we usually talk about weak bases, weak acids, they tend to be the buffers because you don't want something strong that could really change things, right? So what they do is they help to minimize the changes that you see with pH. So a weak base would accept hydrogen protons, a weak acid would donate hydrogen protons, right? And they act as buffers when the environment's getting too acidic, they help to bring it back, right, by binding up a lot of those free protons. Fun fact, if you ever go to Canaveral and they launch, that's a space shuttle, that's an old picture, but whenever they launch a rocket, right, and whenever SpaceX does something, right, all that smoke and all that debris ends up in those retention ponds right around the launch site, and it temporarily brings the pH down pretty low, down to like a 3.5, which is really low, right? There's not a lot of stuff that lives in those ponds. But when you measure pH, it very quickly recovers back to something that is closer to neutral. Any idea what might be going on there? What is the buffer in that case? I'll give you a hint. You're standing on it, although you don't know. Well, it's what your groundwater is surrounded by, right? I know it's hard to think of Florida like this because it's just sandy, but if you dig through that sand long enough, you'll actually hit bedrock, and that bedrock is limestone. And limestone is a carbonate, and carbonate is one of the best buffers you have. So that calcium bicarbonate is actually the thing that helps to buffer water bodies here and helps to keep it around neutral. So when those retention ponds get down to 3.5, well, they come back quickly because all of that calcium carbonate acts as a base, right? It's a base that acts to buffer it. So you see these buffers not only in nature like this, but also in physiology, right? And of course, if you're interested, animal physiology is a class you want to be taking. But in physiology, well, what happens when you're breathing, for example, right? Well, in physiology, you know that you breathe in oxygen, you use it, you produce carbon dioxide. Your body actually doesn't even monitor oxygen levels. It monitors carbon dioxide levels. And the way it does this is whenever you hold your breath, well, carbon loves to be in water, right? It's highly soluble in water. And your blood is water. But when it gets in the water, it very quickly forms a carbonic acid, H2CO3. And carbonic acid is an acid and does what acids do, which is it dissociates into H+, right? So under normal circumstances, you would have this bicarbonate ion that would act as a buffer to the H+. right? And as a result of this, you keep your blood at just about neutral, right? When you build up carbon dioxide, what you're doing is you're actually increasing the amounts in your blood, and you're actually making your blood more acidic. Acidosis is what it's called. And that's the signal for you to let out another breath. So if you ever try to hold your breath forever, you won't die. You will eventually breathe because your brain will force you to breathe. You might pass out, but you'll still be alive. So whenever my kids threaten me with, I'm gonna hold my breath because they want something from a store or whatever, I'm like, yeah, go ahead. Go ahead. Go ahead. I know I'm in no physical danger, and neither are you. So, just a side note, come up with a different strategy. So, the action of buffers is very important, and pH matters, and it matters a lot, and it matters to Florida, and it matters to the ocean. Why does it matter? Well, this is a series of images starting in 1975 all the way to about 2014 of a reef system that has undergone significant changes. Went from being this healthy reef in the 70s with a lot of life in it to eventually just a shadow of the coral that's around now. The reason is because of increasing temperatures, but not really because of the temperature per se. It's because of a process known as ocean acidification. Carbon dioxide levels are increasing. You know this. Carbon dioxide is very soluble in water. That's why when you buy drinks, they're carbonated drinks, right? You never buy an oxygenated drink. It's always a carbonated drink because carbon is very soluble in water. Oxygen is not. And as part of the natural carbon cycle, which we'll talk about later on, carbon dioxide dissolves into water where it forms carbonic acid, H2CO3. This is a natural process, just like it's happening inside the blood, right? The same thing is happening in the ocean. And acids do what acids do, which is they release protons, right? And they form carbonate, HCO3, right? Or bicarbonate, sorry, HCO3 minus. These free protons move around. And under normal circumstances, they can react with carbonate. And when they react with carbonate, they form bicarbonate, right? So they react with CO3, 2 minus. And when they do this, they become HCO3 minus, right? It's a reversible reaction that comes back and forth. So under normal circumstances, it is no problem at all, right? They're reacting with the carbonate ion, and they're forming bicarbonate, and this has always been happening. But with CO2 levels increasing, as they have, and you're having more of this process happen, well, that's actually using up a little more carbonate than it used to use because there's just more of it. So it sets up a bit of a competition between the carbon dioxide that's being dissolved in the water and the shellfish, so coral, which use it for their outer extremities. They use carbonate to build sort of their structure, their homes. Shells, right, mollusk shells, they're produced from carbonate as well. So they need free carbonate to do this. But there's less and less carbonate in the water because there's essentially a competition between the CO2 and the free carbonate that then binds to calcium to form calcium carbonate, which is what makes the shells possible for these animals, right? So this was always happening, and it was always happening at a nice equilibrium, and there was always enough to go around. But now, with more CO2, it's setting up this indirect competition. So this is one of the concerns with ocean acidification. It's what happened at Carey's Ford Reef, and it's happening all over the world. So with that, I will catch you on the flip side. Have a good one.